Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman, and I'm the Marketing Director here at the Academy. Today's webinar, titled Multifunctional Membranes Towards PFAS Remediation. This is the third of 4 webinars in our PFAS series. Our Executive Director, Dr. Daniel Oather, will serve as the moderator and will introduce our speaker today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. We will do our best to address each question at the end of the presentation. Before we get started, Dan would like to say a few words. Dan, how are you doing?
I'm doing fantastic. Hey there, Marissa. Thanks. And thanks everyone for joining us today. As Marissa mentioned, this is the third webinar in a series of 4 with a focus on PFAS. The Academy is offering this series to help our members understand the science and the engineering of managing the risks of these important compounds. And that's part of the value proposition of the Academy. We have members from across scientific disciplines and from subdisciplines of engineering specialization. As an organization that brings all aspects of environmental engineering and science together, the Academy is well positioned to serve as a thought leader in these emerging areas. Our goal is simple: to support you in your work. And of course, one of the ways we do that is by technical programming such as today's webinar. As we begin today's webinar, I want to take a moment to offer some thanks. Specifically, I'd like to thank our patrons. Patrons are organizations who see tremendous value in the work of the Academy and provide the financial support, $6,000 from utilities and $8,000 from private firms, which help us bring exceptional programming to our members. So please join me in thanking our patrons. And if you have an interest in knowing more about how your organization could become a patron, please let us know. And now let's get started. Today, I am thrilled to join you to moderate what I know will be an exceptionally informative webinar entitled Multifunctional Membranes Towards PFAS Remediation. Our speaker is Dr. DB, or Dr. Bhattacharya. He's a university alumni chair professor, director of the Center of Membrane Science in the Department of Chemical and Materials Engineering at the University of Kentucky. DB is a fellow of AICHE. He's also a fellow of the North American Membrane Society, and in 2023, he received the Alan S. Michaels Award for Innovation in Membrane Science and Technology. Recently, he was elected as a fellow of the National Academy of Inventors, a highly prestigious accomplishment. DB received his doctorate from the Illinois Institute of Technology, his master's from Northwestern University, and his BS from Jadavpur University. His CV includes time spent working in industry, recognition of his work with patents, and numerous awards and accolades. We are truly grateful for the opportunity to learn from him today. And it's my distinct pleasure to introduce Dr. Bhattacharya in this webinar. Before we begin, as a reminder, please put your questions in the QA function, and I'll use these as part of a moderated discussion at the end of today's presentation. And now, with those instructions, DB, my friend, the stage is yours. We're excited to hear from you.
Thank you very much, and Dan, for the great introduction. And thank Marissa for also taking care of so many logistics. Without you, would never do these things. Again, welcome, and I'm very privileged to be here. And good morning to some of you in California. Good afternoon to some of you, depending where you are. And if you want to move to Lexington, Kentucky, it was -1 degree this morning. So hopefully I will, as I go through, and you will enjoy some of the aspects of particularly remediation and solutions. So this kind of work is not possible by one person. Everybody calls me DB, okay? You are more than welcome. So a lot of my students sitting there, Sam Thompson, Raleigh Mills graduated recently, undergraduates, Jennifer Bakowski, then Dr. Guttridge, and then, of course, faculty, Dr. Kelly Pennell. We have a UK SRP center here. So we do a lot of PFAS work, not just total solution, but also toxicology. So if you degrade, how much you should degrade? And do you oxidize? Do you reduce? So we know toxicology. And then we have Dr. Escobar there. You can see Dr. Ormsby, about civil engineering. And you can see electrical engineering, also membrane company, and also projects with Chevron and Honeywell, NIMETS, and Southern Power Company. So NIH, NSA, Southern Company, Atmos are all involved here. So I'll give a quick lecture outline. Now I want to show you in the bottom there. You're talking about President, drill, baby, drill, baby. I say, clean water, baby, clean water. And so I also let you know that the water is as important as oil, maybe more important. And every time I produce oil, you produce water also. So I will not dwell too much on how bad is PFAS is. There's so much literature, but I'll give you a few slides. And you have already heard from other people, PFAS aspects. Then bring up membranes. What area is good, what can be done. Suppose you're a membrane company, maybe you want to develop some new areas, what that should be. And some new nanofiltration approaches. These are lower pressure. So you don't want to go to a 700 PSI operation to remove PFAS. Then other approaches, maybe you'll adsorb. We'll take a filter or a membrane thick pore. Can I do things inside which will adsorb and desorb better than activated carbon, because I could apply convective flow, not diffusion. So look at some temperature responsive to amine functionalized membranes and fibers. Then look at some remediation aspects. Also, how you should develop catalyst to potentially hydrogenate, let's say PFAS to octanoic acid, which is non-toxic. So some of the things are open. And also keep in mind that when you talk about PFAS, the water will have other junk, other things. Those could be more problem than the PFAS itself. So what do you do with some of those contaminations? So you may have to remove PFAS and other haloorganics simultaneously. So I got a slide from student Sam and also Dr. Gutierrez. So this you have seen in the left. You can have a groundwater. Then you got landfill is a big area. Maybe you should do a source control before it goes to the water treatment plant. In that, you'll have a smaller plant actually. And households of various places are going to generate PFAS water. And we already know where it's come from. A lot of these have been used, including consumer product, landfill, water treatment, dry cleaners, consumers. But quite often you might end up with other haloorganics or other metals, could be calcium. You might say, why do I worry about hardness? Well, hardness could affect the results of your PFAS capture somewhere. So Professor Dr. Angela Gutierrez actually created in Kentucky, we have in landfill point source funding, you can look at the y-axis up to 500 ppbs. This is Vermont, this is Michigan. A lot of these PFAS components are present. And so you have to look at municipal waste treatment plant water and also a landfill to source control. If we do that, I think we'll manage the burden of treatment to various places. So this has a reference there. When you send you the slides, you'll see it. And 18% of total PFAS load in water treatment plants and 10 times more concentrated. So think of that. Before you can bring it down to 40 ppd somewhere, maybe do a source control where the concentration is a lot higher actually. Various remediation. We are looking at University of Kentucky. I'll let you know. We have a big group. And I told you Dr. Kenny Pellel, Director, UK-SRP. We have toxicology group. We have several students. We're looking at both, not break it down to HF and carbon dioxide, but how to detoxify and how to know what is less toxic. So various technologies have been used. Obviously, if I concentrate the water down to smaller volume, I can use a lot of other technologies of detoxification. And besides, membranes are used to concentrate. Could be plasma, could be high temperature. We're going to look at lower temperature. How do I lower the temperature? Using catalyst. Maybe palladium, rhodium. Can I immobilize the catalyst? Can I reduce the cost? So on the right side, there are some technology listed there. And how do you potentially not only concentrate, but how to detoxify? And how do you know how much you detoxified? Second thing can be known in the water area. There are people looking at now in municipal water recovering fertilizer. Maybe you're worried about where is the PFAS going to go on that one. So obviously need for natural resources, potable water, that could be raw material, it could pay off. So somewhere, if you have PFAS containing higher concentration of water, maybe you want to look at, is there something I can recover there also? It gives you value. Now, of course, by treating this thing, membrane is well known for desalination to removing organics, but the problem will come in, I'll show you that can you take a high pressure RO membrane just to remove from dilute PFAS? May not be a good idea because it costs you money actually. So I hope I was able to give you ideas on PFAS contamination, problems, higher concentration, and could be depend where you apply the technologies. In case you're not very familiar, a lot of membrane, a lot of companies are involved, Torre, Dow Chemical, Femtech, Halogenated, and lots of companies. Some make smallly ultrafiltration membrane. On the left side of the picture, these are dense membrane. So you can, when I say reverse osmosis, there's brackish water, seawater, also the membranes. How do you choose one, okay? You don't want to apply 1,000 PSI to get water through because you may not be interested in removing sodium chloride. But if calcium, other thing present, it could foul also. So nanofiltration, on the other hand, you can have a low calcium, a low sodium reaction, so you don't need to worry about as much osmotic pressures. Ultrafiltration, I may have to pre-treat. The water may have bacteria. Think of the landfill other places. And may have virus. So you don't want to just remove PFAS. You have to remove other things also. I may have to remove particles, or is microfiltration sitting there. So some pretreatment may be required. What about functional? This area is very well known in the area of biological sciences. You can functionalize material, the natural material, including our body. We have a lot of functionalized domain. We respond. My skin is elastic, not as good as young people probably. And so a lot of things are basically responsive. So can I create adsorptive responsive membrane which activated carbon is not? Or I can change some conditions to capture release. And hopefully I will convince you that this is not just come from environmental area, but people know this in pharmaceutical, biomedical, drug delivery areas also. Can you make in situ catalytic particle for detoxification of the target compound like haloorganics and PFAS? How about graphene oxide membranes? A lot of work in these areas. How about bio-inspired membranes? So nature has a lot of examples we can borrow, apply to conventional field, and make fantastic improvement and probably create money-making technologies also. So hopefully people who are sitting in the company here in this audience will look at that, not to just take the desk RO membrane, hey, I'm going to apply for PFAS. It could remove a good job, but you're going to remove everything else. Maybe nobody asked you to remove everything. And so why do I want to remove the hardness if I don't want to remove it? Okay. So those are concerns come in. So it is not applying a high pressure RO or certain NF, how to consider those things. Just a quick background. If you are a membrane company sitting there, people are applying, you and I can membrane tomorrow morning in the lab, I can teach you. But you may not be able to make a reproducible membrane which you can sell and last for 10 years. So typically what you do, you take a support membrane, you can see that like ultrafiltration. These membranes are used for dairy separations. For example, when you buy milk, fat-free milk, or concentrated protein, you buy milk, those are gone through those membranes. So there are companies who's making those membranes for dairy applications. Now, I'm not going to bring up whether dairy has PFAS or not. And that's a different area. Then on top of that, you make a very thin layer of a dense membrane by simple reaction between a solvent phase and an amine. For NF, you use a piperazine. For RO, you use a metaphenyl diamine. It reacts instantly from a thin film. The reason thin film is important, as you'll have high pressure drop, high pressure required. So this is well known by companies, Dow Chemical, Femtech, Torre, Hydronautics, they are all of them know how to make this thing. So these are commercial, but a lot of new thing coming up. Can I put additives? Can I change the formulation to membrane which has a high PFAS rejection? Can I make a membrane where calcium may go through, but not PFAS? These are the kind of things some companies need to be looking, not just taking self-membrane and say, this is going to apply to PFAS, because you're going to remove other things. So in case you're not familiar, you can set up a membrane system in your pilot plant very quickly. You need some pretreatment pumps, modules. You'll have a retented stream. I use the wrong word, probably concentrate, retented, permeate, maybe low PFAS, pressure. So suppose you have a water containing a lot of salt and very dilute PFAS. The salt is going to cost you money, because if you use RO membrane, it's going to reject it even if you don't like it. But if you use the NF membrane, maybe I want the salt to go through. Just reject the PFAS and concentrate. So osmotic pressure will come in the picture not from the PFAS, delta pi, but from other things may be present which one needs to address. And then how do I reject high PFAS? Can I reject 99.9? May not be possible. But dilute solution PPB level, can I go to 4 ppt in one step? Don't know the answer. But you can get easily from 95 to 99.9 through membranes, or selective membranes, commercial or improvement. So keep this in mind with the red color here. No place to dispose retented. And we might need hybrid processes. If you have something in the water, you can recover the material. That could pay off certain things. So here I saw in the audience, maybe there could be some people from Los Angeles area. Unfortunately, what happening in the fire there. But they have the Orange County has the best treatment plant. Used to call Factory 21 in old days. And I don't know, they are looking at PFAS now or not, converting purified secondary sewage treatment water to drinking water almost. Because solid dual media UV membranes, filtration. And so this is a proven, they have recorded, they have shown that running for years and years, a lot of data. So maybe one of the questions someone will ask us, are they looking at PFAS in the treatment train, what is happening and what is coming out? So if you're in the audience from the Orange County, please, I might ask you the question. So here's a little review, lots of articles published. I don't want to dwell with you. You can look at this reference, and that's a 2024 also. So a lot of RO, this includes Film Tech, Torres, all those places, NF, RO, negatively charged NF, showing rejection ranging from, depend which you use, 99% to 90%. But what is the problem? P4 is bigger, I'll show you. But let's say you got PA, BA, lower chain. Those will have a lower rejection. So maybe what I need here, adsorption area somewhere, the permeate may have to go through another system, which is a higher capture capacity of the lower molecular PFAS. Then question, what do you do with the retented? Retented will take that and provide a total solution by detoxifying with catalyst near room temperature. Detoxifying doesn't mean breaking it down completely. It could be oxidation. You don't want to produce fluoroacetic acid. So question is, if I replace the F by H other thing, can I reduce toxicity? So keep this in mind, there's a lot of data. Now, in case you're not familiar, you can buy a lot of modules. It says Osmosis GE. You can build you can quickly check membranes in these little cells or see-through cells, or build a system on your labs of rudimentary systems. Or you can buy and have a company. We did to the Starly Tech company. They built it for us. This costs about, I don't know, $45,000. Completely automated, put RO, NF modules on the top and modules. You can run this and go away. And if you do a lab experiment, generate too much PFAS. So you can really get a lot of data here and make your own membranes or module run 2-3 different modules simultaneously, or small system in a cross-flow mode. So having these things is very important actually, including temperature controls. So, and I'm not plugging for companies, you can build your own, have a completely automated system. You can bring AI, process control. You can sit in Hawaii and can run the plant, run this pilot plant. So I don't know bringing math at this point, but membrane separation, membrane may have charge group, may have activity coefficient difference, diffusivity, then diffusion concentration gradient, and charge, even for RO. So this could play a role. PFAS has negative charge at the end and a hydrophobic domain. Give you an idea, calcium, sodium is about 5 angstrom hydrated size. PFAS depends how you look at it. This way, it is maybe 10 angstrom lengthwise, and then diameter maybe 5 angstrom. So it depends how you align, okay? So charge, diffusivity, other thing going to play a role in convective transport. Now let's go back a little bit. Suppose you got water. We might have to worry about, besides PFAS, maybe other chloroorganics. Other components could be there. What do you do with those? Is water segregation possible? Suppose I'm an industry. Shall I segregate some water out from something? What about heavy metals, other thing present? Well, membrane may remove that, may do so. Suppose there's a trace amount of arsenic in that water along with PFAS. And what about fouling component? Scale component. So if you remove the hardness by the membrane, you could form scale. And the cost of the process is not for PFAS treatment, but for other things are there. So high concentration of dissolved solids has to be considered. Do I want it to go through, suppose you got 100 ppm sodium chloride, 200, maybe it goes through, or do I want to recover? Is material recovery desired? And what are you going to do with the water? If I'm discharging it, I have to get a permit, reuse it, or do I need a hybrid system? Maybe I need activated carbon ion exchanger with that. And how clean is clean? Well, I don't think any membrane can bring it down to 4 ppt without using other functionalized approaches. That is not trivial. So again, summarizing, our goal is to concentrate and also detoxify, providing a total solutions. So at the University of Kentucky, we have groups from toxicology to civil engineering, chemical engineering, electrical engineering, we work together. So some nanofiltration advantage towards PFAS. I'm going to state of their knowledge. In case you want to make it, it's very simple actually. In the lab, you can make one, may not reproduce. You take two solutions, one in water, amine, and one is trimethyl chloride and a solvent. The two partitions and have a backing membrane of ultrafiltration. You cast it, and that's a piperazine. Or you can make positive charge, putting polyallyl amine. You can make negative charge membrane, positive charge membranes. Lots of articles, not only us, other people. And you can look at that one here in the bottom. I had a brilliant student, Francisco Lenis, who did some of this work also. He's now at BASF. So this one, this came out 2 weeks ago. So maybe the audience, I happen to be a reviewer for this, I'll let you know that since it's published. It is a combined work between China and Australia on modifying NM membrane making principle rather than just using the water and amine, put ethanol to create nano bubbles and high heat of reactions. They showed, this just came out by the way, in Journal of Membrane Science, that using ethanol or a co-solvent in the amine, you get more I call wrinkled membranes in essence, with a fairly high flux. Flux we call in the membrane industry LMH per bar, or LMH, liters per square meter per hour. So like RO membrane commercial, that number could be LMH per bar, could be 1, very tight. Microfiltration could be 2000 LMH per bar. And these ones about 15. NF could be 5 to 20 LMH per bar. So obviously higher the LMH per bar, and you can reject, you save a lot of money. And maybe you don't remove everything else. So this one shows there, they use 22 PFAS mixtures from small PABA, low molecular weight, to PFOA, PFAS. So you can see, and the NF270 sitting in the corner, one of the color, the purple, I think, that's the commercial Dow membrane, which everybody compares in essence. So you can see the presence of ethanol this case, the little higher ethanol form in high concentration during the membrane making. The solution has no ethanol. You can see that even PABA got a high rejection, 92%, 95%. And you can see that PFOA and other things are rejecting close to 99.9% area actually. And so keep in mind there are a lot of advancement going on. And note NF270 is a benchmark Dow NF membrane. So ethanol doesn't mean I'm adding ethanol to the water, by the way. This is during the membrane manufacturing. So it is gone. At the end, ethanol is not there. And demonstrated 99% rejection of sodium sulfate. Now, if you got calcium there, you could precipitate. You know, that people didn't consider possibly. And you get rejections of 93% to 99.99% for 22 PFAS compounds. So I'll strongly encourage you to look at this article. When I submit the slides, you will see that actually. Another elegant work did by many Elimelech group in Yale, and of course, as you know, he's in Yale, recently left Yale, joining Rice. I don't know if I'm supposed to say it or not, but it's a smart group. They try to make a membrane for removing PFAS, but how to lower the calcium rejection so you don't form scales. Brilliant approach. So companies sitting there, please think of those things. We cannot just leave on the regular NF membrane. Can I have something go through? Because I don't want the water with a very low hardness. So they added, see this, piperazine is used and bipiperidine. The goal was to get a membrane which rejects PFOA, not 99%, still 90%, allowing high passage of calcium. That is not trivial. And so normal commercial membrane reject calcium 90%. So keep in mind, sodium goes through, but calcium retaining in RO membrane, this will reject 99.9%. You can reject everything. So question is that, why do I spend money rejecting everything? And if I don't need to. So keep those in mind. On PFAS treatment, when you do work with the landfill leachate or other areas, you have to think about those. So new approach. Hey, maybe we'll take a filter or membrane thick and we will functionalize the pores, apply lower pressure like microfilters or membrane, and capture learning from natural sciences field and responsive membrane field. People have used this, you know. Can I shape control the pore? Pore could be changing 2-3-fold by changing 1 degree, 2 degree temperature or pH. These we learn from life sciences field. So I'll show you temperature swing, pore function as amine, a lot of activities. We'll show hydrogel. I have some students, Raleigh Mills, Anthony Saad, Sam Thompson, Subrajit Bose, all of them looking at and captured at the University of Kentucky. And then also look at, can I use a nanofiber electrospun membrane, which has a very low pressure operation, almost 1 bar, with covalently attaching quaternary amines. So P4 is a long chain hydrophobic, with likes could be hydrophobic domain and a charge. One side is long and the other side is short. So obviously, even RO membrane and if you can align proper way, I get 100% ejections. So you're also looking at how to change alignment of PFAS through membrane morphology. But in this case, you're going to capture and some cases remove. So responsive membrane, nature knows you can have a T is responsive material, temperature. Well, you and I are temperature responsive, obviously, because we know when I walk this morning, it's cold, and my ear almost getting frozen. And then when I come inside the building, I'm good. But there are a lot of temperature responsive material used for drug delivery system. Magnetic responsive, light. There are people who have done work, when I search light, I can change material from hydrophilic to hydrophobic. Search it. And then electric field I can apply. pH ionic strength, I can change and open pores of membranes. An enzyme substrate. So we want to use simple non-toxic chemistry to functionalize the backing of the membrane, which is very open, to capture PFAS then modulate the temperature or the pH to regenerate and create a highly concentrated solution which can be catalytically detoxified. That's the goal. Let you know, we don't live in a vacuum. It is thanks to actually many, but those who've been Selecta. Now, that's company I worked with. They're a wonderful company in Oceanside. I lived in Oceanside, California, beautiful place outside San Diego. That's what a lot of membrane companies are. You can make it in the lab. You can do a full-scale roll-to-roll operations. Then make a module. And then you can convectically, the back, this is a microfiltration membrane. We functionalize the inside with whatever you want, the temperature or pH, and then you can attach things afterwards. So this lets you know that this can be done actually. We have a roll-to-roll processing, and you are looking at an example. This is not just a picture. This has been done actually. So let you know that before I go to PFAS, we also work with the Chevron company, Dr. Evan Hatakiyama. So that suppose the water has mercury dilute amount. Let you know we can change the functionalizing. For the case of PFAS, we might put amine group there or something else. But I could put SH groups here. Instead of ion exchange, this captures mercury, silver, other things very effectively. You can look at the publication, and Dr. Evan Hatakiyama is in Chevron, then Dr. Saiful Islam, Dr. Hernandez in Australia right now. They are my PhD students. You can see mercury capture is almost 100%. Very dilute, and go from maybe 5 ppb to less than 0.1 ppb. So you don't need to regenerate naturally. We capture silver, of course, and gold, you can regenerate and recover. So let you know, the functionalizing for PFAS, you can use amines and other things. But in the case of metals, I might use something else. To show you that it is indeed responsive. So on the full-scale membrane, quite some time ago, Dr. Takigawa with a Selecta. So we put both carboxyl groups and temperature responsive NIPAM, pNIPAM. You can see the membrane water flow, I can change near 32 degrees, not because of viscosity. This is PVDF MF membrane by several fold. So I can modulate the flow through the membrane and rejections by changing temperature and pH, as demonstrated that this, without functionalizing this PVDF membrane, is not responsive. We could use PES membrane. We don't not married to PVDF and other things, So let you know that this is a full-scale membrane he made actually. Now let's go to PFAS. Now, the water I'm drinking, I don't know, I got it from the outside. Our tap water, they claim they have an RO unit, may have PFAS. Hopefully not much, below 4 ppt. Lexington water is pretty good, I think. And because we do a pretty good job here, like other places. So converting traditional microfiltration membranes, which could be pore of 400 nanometer to 1 micron, do something inside, not waste it, to capture release. We call using this one example we call TSA, is known in the gas industry, temperature swing, adsorption-desorption. Normally in activated carbon, if you increase temperature, adsorption goes down actually. But these compounds I'll show you using NIPAM, which is used for drug delivery systems. You can change your body temperature 32 degrees. It goes from hydrophobic to hydrophilic. This is not our inventions. So let's say this compound here, P4, this part is hydrophobic. Of course, this part. Ideally, you can have both. So in this case, I don't need high temperature regenerations. But having brilliant students and collaborator, Dr. Ormsby, Dr. Saad, Dr. Ollie Mills, he graduated. He was a superstar, our UK SRC program, got all big awards from UK SRP national levels, and recently published in Applied Materials, Interfaces, and Membrane Science, and we also have US patent. I want to bring up the patent. Right now, as we talk, we are scaling up. I work with a start in Singapore to hollow fiber domain module, getting a really high capacity for PFAS capture. So we're really scaling up to a larger scale, not just flat sheet, but hollow fiber domain. it using start in Singapore, where I go there once a year. So let you know, literature. This is somebody else, I forgot the reference here. In physical chemistry published that pNIPAM structure, which has a isopropyl group on the top, I don't know what my mouse is, right here, and the hydrophilic group. If you change temperature, LCST, lower critical solution, it goes from big hydrogel to small. Swells. This property you took advantage of, and that's the reason we got the patent actually. So controllable, you can change other temperature if you want, go to 25. Conformation change, getting character. So going from below LCST, lower critical solution temperature, to higher, you can change the conformation inside. So in this case, above this temperature, hydrophobic, you'll absorb the PFAS. If I lower the temperature, you'll demonstrate that it will release it actually. So I can get a concentration factor, maybe 20, 30, 40-fold. That's the goal. You don't want to detoxify water, million gallon. You know, detoxify only maybe 10 gallons or 100 gallons. To show you that, traditional civil engineers know those things. This is a PFAS sorption in a hydrogel, pNIPAM, that compound. One is, say this one is adsorption done about at 35 degrees C, at 32, and below is LCST. So it is absorbing quickly. And then when you lower the temperature, I can dissolve. And this kind of model has been proposed, it works. So in case you're not familiar, this is a high value of my key equilibrium adsorption of PFAS at 35. Look at that, 48 versus 11. Why? Because I created hydrophobic domain at the temperature above the LCST and hydrophilic. So I'm changing gating property of the inside, and the hydrogel doesn't come out from the membrane pore. But this could be hydrogel by itself. You don't need a membrane necessarily. One of the way, if you are good in polymer chemistry, you can describe molecule by solubility parameter called Hansen parameter, Hilderman, which is hydrogen bonding, dipole-dipole interaction, dispersion parameter. This is important for the fluorocarbon-fluoro chain. So you can take advantage of those things to design systems which will enhance. You don't want to capture so strong that you can release thing. You can select it almost threefold, and the pore getting bigger because the hydrogel collapsing inside the pore become hydrophobic. So at 32 degrees C or approximately, I'm absorbing PFAS. I could dissolve more. The lower the temperature, it dissolves. Absorb, dissolve. So these are used by chemical industries called TSA and PSA for removing gases actually. So let you know that you can get a concentrated solution depending how it dissolves. Now during the desorption cycle, we could put some methanol if we wanted to. So to show you that the membrane containing pore with this temperature responsive polymer, I'm absorbing and creating a concentrated solution with resorptions. So my goal is to pass 100,000 gallons and end up with a maybe 100 gallon. That's ideal, of course. Then you can detoxify. You can also do, having some brilliant people in the labs, and one of them was Francisco Lenis. We have done, so you can say, why not take those membrane and put an NF layer on the top on a microfiltration? We believe nobody has done it. So we can exclude some of the junk out, like the larger NOMS organics or other things. And only remaining small PFAS will get absorbed in the backing containing the pNIPAM or amine, which you can regenerate if I wanted to. So we put things on NF, on MF membrane, which is functionalized. And we believe that other people have thought of that, obviously, but we've been successful. And and you can look at one of the articles in SCA's Applied Materials. and also in Journal of Membrane Science. To show you, this was common EST water. Now, we could not make a perfect membrane yet, but look at that. This is P4 rejection. So the background now, absorbing some, we could actually regenerate. So this is combined NF and functionalized membrane of pNIPAM in this case. So we take NF270 Dow membrane, Dow type membrane, polyamide. It is not temperature responsive, but this membrane is temperature responsive. You can see amount adsorbed P4 per amount of membrane is obviously high for these compounds, but normal NF membrane doesn't have any adsorptive capacity. So you can look at that EST water article. There's another instrument you want to buy probably. We found out, I'm glad I did that, this is used in dialysis area. You can get called Parmagia. I think we paid, just to give an idea, about maybe 42,000. This has multiple cells, could be 3D design. Small cells, you can do diffusive permeability of membrane. So you can put maybe 1,000 microliter, and you do a diffusive permeability. So under diffusion, no convective flow, how much PFAS go through the membrane? That's a good test. You can do hundreds of samples quickly here. So you can see that that's P4. So P4 is this is a diffusive permeability, not convective flow. See, diffusive only. And some NF membrane, sodium sulfate, has a very low diffusive permeability because it rejects charged groups. And so keep in mind, so the 10⁻⁷ diffusive permeability of P4, that'll give an idea under diffusion condition that the small chain, big chain goes through. So I can now create a better membrane having those kind of data actually. So you're not applying any convective flow here. Now, thanks to brilliant student and research engineers, Sam Thompson, Angela Goodrich, Jennifer, undergraduates. This was just published in Molecules. So then you say what you'll do, we'll put quaternary amine or primary amine hydrogel inside the membrane, but not covalently attached. Then capture, release by changing pH in the case of primary amine. That's an advantage. Or quaternary amine, you have to use salt and some ethanol. Here is the flux data. You can see high flux membrane. This is functionalized. You're getting almost, some cases, 1,000 LMH at 3 bar. 1,000 LMH, liter per square meter per hour per bar. In RO membrane, those numbers are 1 LMH per bar. That means you require humongous membrane area. We are capturing, not necessarily rejecting in this case. So this is the detailed chemistry, and you have to look at it more, finding out how we did it. To show you that indeed works in molecules, again, thanks to our big group of people here at the University of Kentucky Superfund Research Center and Membrane Center. So this is P4, left side. Right side is PFBA. Quaternary amine, primary amine. Nobody has data on primary amine. So it's adsorbing, what do you do? Capture, then release. Concentrating it. It does work. We saw through several cycles here. And also you can see this is PFBA, capturing, releasing. We can optimize it, obviously. And so in this case, we go to pH above 9.5. You can release some of the PFAS because primary amine is not ionized at that point. But quaternary amine, you're going to pH 11, obviously. To show that indeed, and look at the flux values, 1,500 to 900 LMH. These are almost loose ultrafiltration, microfiltration membranes. But inside, it contains valuable material, simple amines, hydrogels. Then he said, why not? I had a brilliant student, Dr. Wan. He actually got his PhD here, worked with the UK SRP, and he is now in China. He's a professor at Hunan Technology. So joint work with them, recently published as in 2022. But in this case, what he do to the membrane, PVDF, and attach the quaternary amine covalently through electrospun fiber by the membrane. The fibers are 20 nanometer to 50 nanometer. So fibers containing amines covalently attached In this case, we did not attach covalently. Covalently means to the membrane surface. So you can see you get hydrophobic domain and hydrophilic domain, and these are the P4 rejections and PFAS. P4 and also sulfonate. And so rejections and then high conductivity water, you lose some, obviously. So other compound like organic humic acid may come in the picture. So this is a low pressure, gravity driven electrospun membranes for this PFAS. And let's see, now this same material to show the effect of humic acid, charged surfactant, anionic surfactant, other compounds, could be octanoic acid, organic amines. So you can see there's some loss, particularly for PFAS. We do lose some rejection behavior when other components are present. And you can see the publication of membrane science and in chemical journal. Another approach, we did hydrogel, the amine, quaternary amine, but hydrogel, but you can also covalently attach, same principle on a membrane, but covalent. And you can see P4, these are pH, adsorbing, dissolving, at pH 11 does not adsorb. And you can see several cycles, amount adsorbed in this case, treatment volume, cycle 1, cycle 2, cycle 3, and then also, of course, we desorb at pH 12.5 and 5% methanol, and got about 98% desorption at room temperature. And so approaches getting that, you cannot do any of those things in activated carbon. So you now we can maybe concentrate, reject, capture using knowledge from nature. Nature is highly responsible. So can you do things when it captures the material change? So now that it's concentrated, we'll discuss some going on in this area. Or I will not be able to give you a lot of detail because you have some things working on, and maybe another webinar down the road somewhere, you'll get to know more. Palladium, rhodium, those areas known to detoxify compounds, hydrogenate at room temperature using hydrogen gas. We might use iron or silica support membrane, but people making mistakes that if you make a solution phase, you lose. Our goal is to it be captured in a polymer domain. So when you supply the hydrogen gas, you don't lose any of the catalyst. So a catalyst could be nanometer particles attached to something, could be iron or silica, and then you don't lose it. And otherwise you'll go bankrupt. And then of course we can supply hydrogen gas through the membrane, creating nano bubbles, high mass transfer rates. So elegant work from Long and Bruce from ASU. They have demonstrated that palladium in this kind of membrane, hydrogen gas, you can hydrogenate part of P4. Not completely. We also know that we can make small palladium in a Fe domain inside the polymer pore, or hydrogen will come in. In that way, I keep the catalyst constrained. I could also apply higher temperature, 45 degrees C, to increase the action rate. So question is that, how much hydrogenation do I require to reduce toxicity? Obviously, ultimate to make octanoic acid, And so the role of catalyst and how to increase mass transfer of hydrogen is very recently published. Bruce Littman's group, they found out that using rhodium, palladium rhodium, they could get a hydrogenation of some of the PFAS compound. I think they use P4, and using combination of palladium and rhodium. Okay, so this was published in EST Engineering. I think just came out, I don't know, a month or two ago. Very nice work, and they applied the hydrogen gas to a hollow fiber module, putting bubbles, small, nice work. And so basically hydro defluorination could be done. So our goal is to provide total solution. We cannot throw out the retented from RONF back to someplace. There's no place to throw things. I tell my students, that assume you can't throw anything anywhere, what are you going to do? You know, and so you have to keep this in mind. If we try to treat the million gallon of water in a water treatment plant by catalysis, you will go bankrupt, I think, because there'll be too much water. It is good to concentrate or use the source control. That's our approach also. And reduce the loading of PFAS to system drains. So over the years, thanks to brilliant student and again our UK-SRP, NSF, other things, I'll not go through. It is so easy. Probably I could teach you in one day. You can take a pour some membranes of material. It has convective flow. You put some, in this case, you put polyalkylic acid. Capture sodium. In this case, iron could be something else. We made iron zero, borohydride. Then iron zero and palladium chloride can displace for minute palladium nano size sticking. The size of the catalyst is about 20 nanometer. Dr. One did the ACM cross section. This is the thickness of the membrane, about 100 micron, with 20 nanometer particles inside. We did cross section, focused ion beam. Then showed that on the right side, this happened to be PCB. We did a convective flow approach. Membrane contains this polychlorobiphenyl. We halogenated completely in 45 seconds. And I'm telling you, we're going to show results on PFAS from halogenation. The approach, the goal will be to how to supply the halogen properly. But we know how to create catalysts. We have not done rhodium yet, but this principle is keeping the catalyst immobilized so you don't get deactivated by junk compounds in the water. It's critical probably. Another approach making catalyst. So we said you're making by solution phase. Now you need people from material science, and brilliant student, Dr. Mike Ditz, Dr. John Bulk. He's a physicist, my PhD student, physics and material science. Not an environmental engineer. We taught him haloorganics, and he taught me physics. And Dr. Bulk. So magnetron sputtering deposition is known, by the way. So we can take a membrane pores, the surface, like ultrafiltration membrane polysulfone. Don't worry about the small tantalum. We can put little magnesium palladium deposit coming in, very minute upon, could be 10 nanometer, 20 nanometer layer on the top, very small amount of palladium or rhodium. And then it dissolve away the magnesium, keep the palladium porous. So the solution goes through, can I hydrogenate if I supply hydrogen gas? Now, if it didn't work, I will not be talking to you today. And otherwise, he'll not get PhD and publications also. So we do a commercial membrane, select a PS35. This is a dairy ultrafiltration membrane. And on the top, we deposit it. And this is highly solvent membrane. And so to show you that this is a membrane, this is you got a very small palladium layer there. But highly ligament size is 4.1 nanometer. So when you apply the water on the top going to be there containing PFAS, or in this case, chloroorganics we did. And then we actually have hydrogen gas tank there, and maybe it will reduce it. So can I go an organic compound, convert the chloride or fluoride? Fluoride, I'm not done on this yet. We're doing it as you talk, hopefully we'll know in a few months. And to show you that how easy to make this. Deposit, magnetron sputtering, catalyst particles, experiments. So here is the hydrogen, of course, Henry's law constants. So we did hydrogenate, actually, very fast. So we looked at the dissolved hydrogen. So question is that hydrogen will come in the picture because hydrogen is not highly soluble in water, obviously. And so the headspace, we pressurized the hydrogen, and we plan to do the similar things for PFAS. And so demonstrate to you that our goal at the university, not just me, I need a lot of collaborating people, Dr. Kelly Pennell, Sam Thompson, previous students, and Dr. Ormsby and Dr. Todd Hastings, and industries, how to bring this to practice in a fuller scale. And so that's the goal, providing a total solution, not just to concentrate and don't worry about what happens to concentrate. So give me some key takeaway messages, maybe hopefully my friends and new friends sitting in the audience. And please feel free to contact me. My email address is very simple, db@uky.edu. I'll be happy to help out on whatever it might be. And if you want to use any of our facilities and our university will be happy to work with you. But some key takeaway messages. What RO, what NF? They're using for desalination membrane. Rejecting salt, 99.6%. Well, high pressure required because the pores could be 5 angstrom, 6 angstroms areas. Do I need that? Maybe we can align the NF PFAS this way rather than this way. NF, can I get some salt, calcium, or some sodium going through so I don't need higher pressure? Can I run at a 1 bar or 2 bar? How do you select? So normally they'll give you sodium sulfate data. Very few companies giving PFAS data. So research needs are needed. If I'm a company, probably I will look into that, how to modify some of the membrane without reinventing chemistry to improve PFAS rejections, but not lowering flux to 1 LMH. Again, LMH is liters per square meter of membrane per hour. Typical RO membrane desalination, they're running at 800, 900 PSI. And obviously, you don't want to run it, it didn't been planned at 900 PSI for PFAS. What about responsive and functionalized membrane, as you discussed? GAC will not do it. So we're applying not just diffusion, but convective transport. Push through, it will capture. No way to do it in a bead. You can have a material adsorptive domain, which has both hydrophobic domain, like pNIPAM, and ion exchange domain, like amine. Detoxify the lower volume regenerant or the retentate, not the entire water, who will go bankrupt or process will fail actually. When you concentrate the regenerant or highly concentrated, I could do any other solvent media if I wanted to, non-toxic. I could bring in other solvents to improve hydrogen absorption capacity. But I cannot do that with a 100 million gallon of water. What is the role of other metrics in water? You cannot forget. You're going to find not only PFAS, but you might find TCE, PCB norms and things there. If you neglect those are the one could be problem maker. Or you may have to hydrogenate the TCE also. There is water where PFAS and TCE, PCE may be present. So need for hybrid technologies. I'm not saying activated carbon is done. Maybe the final step has to go to bringing down from 10 ppt to 4 ppt, so you don't need to regenerate that often. So there is a place for activated carbon, but for dilute solutions. Lots of places funding requires. Big one, SRC. We have an EPSCOR program, which also right now dealing with the charged particles. You have not discussed. The water may have particles, you have to remove it. And some companies and various people listed there. And so with that, I hope I was able to give you not just traditional RONF, beyond that, to provide total solution and selectivity. Otherwise, we will not solve the PFAS problem. Thank you very much.
Thank you, DB. Fantastic presentation. Really appreciate that. Maybe if I'll have you pull down the slide and then people will be able to see us kind of side by side, if that's okay to stop share.
Ah, sure.
You're so kind. You're so kind, my friend.
So I put down the top, stop sharing. The
Yep,
green.
that'll work great.
Okay.
Oh.
Let me see. I've not done it yet.
It's okay. There should be a red button there that says stop share, but that's okay. Not a problem.
Yeah, I got it. It showed up. Delayed.
There you go. There you go.
There you go.
Fantastic. Fantastic presentation. So first of all, I saw those automated systems and I thought, man, to be a grad student or a postdoc in your lab, that would be awesome, right? So you're advertising people can work from the beach
Well,
in
you can do a lot of
Hawaii.
people. Yeah, you can.
No, that was fantastic. So it was really clear that you had a lot of discussion about the selectivity of the membranes, right? And so
Yep.
we've got a really diverse audience, right? Lots of folks coming at it from lots of different places. So help us. One of the things we're going to think about is how do we conceptualize these membranes, the interaction, right? Because we can think about membranes as having these ideas of concentration, polarization, and stuff building up on it, or we can think about it as pores. So let's have a little discussion about how we're conceptualizing the membranes.
Okay.
Then you're talking about the functionalization. You've got MF, you've got RO, but how about FO and how about low pressure? So let's see how that fits in there a little bit and how that compares to other types of techniques for separation, like foam fractionization
Yep.
or other kinds of things, right? And then it was.
Let me stop you for 1 second.
Well, hold, if I can.
My PhD research in when I was in NIH was on foam fractionation.
Fantastic. Good. So you'll handle that one. That's an easy question. So the other one we wanted to some curiosity about is this idea of like the biological mimics. So we heard a prior presentation that was talking about the toxicology and how PFAS sticks with fat or sticks with proteins.
Yeah.
And so kind of looking at the relationship between what you're doing with membranes and how the membranes in our body are interacting with PFAS. So a little bit of what the biological mimicry looks like there. So if you can, speak to that. Some people had some questions about, ultimately destruction, right? So a lot of us think about membranes as producing a good stream and a bad stream. So where does the bad stream go? You address some of that, but we'll come back and address it in particular. Long-term operation, where do the membranes go at end of life? Let's think, LCA type stuff and how do these get destroyed? Multi-barrier, if I'm thinking about drinking water, if I got one membrane, one hole, so if we can answer some of those kinds of questions, and then advice that you might leave with students or emerging professionals on how to get involved in this kind of work. So that's kind of the breadth of things that we would talk about. So up front, right? So how do we?
But you did an outstanding job. I would bring you here. Maybe you can run our. You summarized everything so well.
You're too kind, DB. You're too kind. So let's conceptualize these membranes, right? So we think about low pressure, we think about high pressure, we think about RO, FO, MF, NF. How are you conceptualizing the PFAS and the membranes and then all the other stuff interacting? What's your mental model there?
Okay. Now, obviously, you can make a tight membrane like a high pressure RO. Four sides, things will not go through, but it'll pay a big penalty, rejects everything else also. So constant polarization will come from something else, not from PFAS. And you're going to apply 1000 PSI. So can I create looser membrane? Nature knows how to separate looser membranes where something may go through. I don't want to remove it, but also rejects if I can align the PFAS properly charged. Remember, this way is bigger, that way is shorter. Could do. So basically, there's a room how to go to at least 10 to 30 LMH liter per square meter per hour per bar. That will keep you alive. So if you reject, it has to be thin membrane because pressure drop. If you capture, it could be thicker membrane, a combination. So obviously, and if you make a membrane very thin layer, it may not last more than maybe 6 months because it could scratch away. So there is industries know those things. We have a lot of high-level industries on thin film polymerizations here and grown. So if you go and state-of-the-art seawater membrane, it might reject PFAS 99.999, but at what cost?
Okay. So there's a trade-off. How much we got to push the pressure, how many square feet or how many square meters of membrane we got to have wound up, and then how thick these. Okay, so that makes sense, right? So you've talked about the emphasis on this selectivity. So how about it didn't seem like we heard
and then
about.
Let me complete that. Because the RO retented now will absorb other concentrated calcium along with the PFAS. You're going to create a big problem.
Okay.
So something you don't need to remove is best to go through. Hey, I don't need to soften the water.
Right. How about forward osmosis, FO?
Good point. Nobody has done it, but bottom line, you could. There'll be like a diffusion measurements I gave you on that one, diffusion measurements. And but then you'll end up a PFAS diffusion is going to be very small.
Okay.
Potential exists. Nobody has looked into that part. Maybe a good point.
Okay. Okay. Yeah, because you were talking about, functionalization,
Yeah.
you were talking about
Potential
pore,
exists.
yeah. And then the temperature swing absorption. So how about other techniques, foam fractionization, right? I mean, what if we
But
kind of got
bottom
away
line
from
is that these are surfactants, now the bigger chain. Is obviously it has a micelle. So if I can enhance, I'll tell you that. Foam fractionated, when you bubble it, surfactant is going to go in the bubble phase. I did PhD. My PhD was on foam fractionation. And so we use surfactants in those, not PFAS. So PFAS will go in the phase. You get a concentrated foam, but not necessarily the water will be 4 ppt.
Okay.
Okay. So the foam concentrate, you could now potentially look at detoxification. So I think the approach is good. So basically, one approach we are looking at, what you can do on a surface, you can enhance micelle formation, interaction among the PFAS, so that I can go remove, reject material at low pressure, make it bigger.
Okay. Now, so one of the questions that was here talking about the membranes itself, could you actually imprint the membrane with PFAS, like as a template for some kind of, I'm thinking it kind of sounds like a lock and key type, strategy there, right?
People are looking at fluoro compound, but make sure it doesn't come out. People look at imprinting, that could be interesting area. And taking an exit, don't want to reinvent the wheel. You can also do spray coating, by the way. And so a lot of 3D area come in the picture on the surface. The way those guys from China, Australia got good results, they did a modification of the surface or wrinkle structure.
Okay.
And so your idea or mentioning on the printing aspects could be exciting, actually.
Okay. Okay. No, good. So now if we're going to imagine these membranes kind of, and you were emphasizing a lot of kind of biological mimic, right? And we've had a presentation focusing on the toxicology, like where does the PFAS get into our body and how does it interact? And so we heard a lot about the compounds that make up the membranes in our body, right? The oxynol water coefficient, and how much does it stick to our membranes, and how much does it stick to the serum protein that's in our blood, right? So we've heard about that. How do you use that kind of biological mimicry, that kind of information about how it's interacting in our body? How do you use that when you're thinking about these membranes?
Fantastic question. I'll tell you right now, proud, our membrane center got created because a brilliant person, Dr. Alan Butterfield, we started our membrane center, the biofunctional membranes, all completely not synthetic membrane, bringing biological principle interactions, actually. So obviously, we have done remediation also, detoxification, dechlorination by using enzyme in the membrane, certain kind which will degrade certain compound. But I could attach some biomimetic molecule surface which could have profound impact in essence. That part is definitely, we plan to look more, and that is an area which should be of strong interest, But the thing you have to do, your real water may be a lot of other dirty constituents. So you may have to treat it now in a membrane where everything else go rejected, but the PFAS go through. And then you treat that to this, because otherwise it will ruin the biological molecule, proteins.
No, because
you can take dirty river water and go through their biological system.
Right. Well, there's a lot of parts to it, right? Because biologically active membranes is something to think about, right?
Or you can have bacteria. So I may have a microfiltration membrane to get rid of the bacteria. But we don't know right now, Dan. Hopefully somebody knows in the audience, maybe give the answer. Does bacteria on the surface absorb PFAS?
Okay. No, it makes sense, right? I mean, everybody's trying, we're throwing everything at this one problem, right? So how do we put it all together into a
your
system?
idea is outstanding. The audience is also, Carla did a good job. He's taking understanding from biological toxicology interaction phenomena, those biologists, biochemists in our university, other places, they're top-notch people. And knowing the interaction could help in providing total solution.
Okay. Well, now you kind of dismissed GAC, but how about carbon fiber? Could that be integrated?
I didn't dismiss GAP. What I'm saying is that it has to diffuse inside. You're getting low capacity. If you use a GAC, use a more open structure GAC and go for the final polishing. You don't regenerate. But carbon fiber with the proper functionalization could have a high potential.
Okay. Okay. So that would be one that people are there any groups that are looking particularly at carbon fiber?
How many publications, although I'm not very familiar, could be there. You know.
Okay. Okay. Fantastic.
Now, as you know
Fantastic.
that you can take polymeric material like PA and make carbon fibers out of those. Those are different than bituminous coals.
Sure.
So depend how you make the carbon fiber.
Fair enough. Fair enough. So then how about, if we think classic membrane, right? This goes through, we keep
I'm
it,
going
this
out
doesn't
from
go
classic
through.
membranes, yeah.
Yeah, so we're thinking classic membrane, right? So if we're doing a classic membrane, what do we do with the reject in the PFAS world?
No.
Are we
Now,
stuck?
with a classic membrane, California mandated to ensure that how to recover 98% recovery water. So if seawater is only 50%, concentrate 2 times only. So hopefully seawater doesn't have PFAS. So maybe they're looking at now. So question is that, can I recover by RO membrane 98%, which is 50 times concentrated? Well, how are you going to prevent fouling and constant polarization of other junk?
Mhm.
Okay. So pretreatment may come in the picture.
Okay.
Then after that, you might be able to go to 99%, 98% recovery, concentrated PFAS. Otherwise, your fouling will be immense. No RO membrane exists. If I give a dirty water river and say go to 98% recovery, you're out of your mind.
You'd make a lot of money if you came up with that one,
The
wouldn't you?
pretreatment may require, that's what RO people do, make the
Right.
water cleaner. And
Right.
but maybe I need a membrane, eject the salts and things out. I don't need it. The other membrane, PFAS go through, then use this to concentrate at a low pressure. Maybe I use a low pressure RO, 100
Mhm.
PSI, because PFAS by itself doesn't have much osmotic pressure.
Sure.
So you're bringing up very good points.
Well, and then there's a couple of kind of specific questions in here, right? So, one question was, okay, so what if we went with foam fractionation as a first step? What if we follow with membranes to concentrate the PFAS? What if we start thinking about putting these together in multiple stages? Any suggestions there of things we'd be looking at?
Now, in my tech home question, I had some need for hybrid. So you can take existing process you have. You can change the entire treatment plant. Suppose you already have certain thing. Why can I put my unit in a water treatment plant? Let's say American Water Company here, an example I'm using. And but you're dealing with large volumes of water now. So you're going to, suppose you're going to remove by membrane the millions of gallons of water, you're passing pure water, it's going to cost you a lot of money.
Okay.
So foam fraction is something concentrating that. Further policing is a good approach. Now, I don't know the results right now of the lower molecular PABA and P4. I have a feeling the lower molecular doesn't go to the foam phase. It is not as a fact, it's going to stay in the bottom. So now we need a membrane to remove the lower molecular weight.
Sure.
Emphasis should be there.
No, it makes sense. So we had a real world question, which I'm just going to hit you with to kind of get your impression, right?
Yeah.
So we're looking at groundwater, couple million gallons per day, and thinking about using nanofiltration, and then take the concentrate and do a deep well injection as a way to get rid of the concentrate. Thoughts on that?
Deep well injection containing PFAS. Okay. Now, some places will not give you permit.
Okay.
And question is that what else in their water? You have to worry about that. Suppose that water, some trace of arsenic and other metals there, now that PFAS content will have those things.
Mm-hmm.
So you're going to find a water, so assuming the groundwater has no other contamination.
So you got to focus really on the permit there for that one.
Yeah.
Okay.
So that getting permit will be tough because you have to also prove what else is there.
Okay. How about long term? These membranes that we're using for PFAS, where do they go at end of life? I mean, do we,
I think probably the people look at Germany, there's a lot of work going on. So what happens is that these membranes only create like RO. After some time when you use it, that life of RO, let's say 5-6 years. After that, in the top layer get lower rejection, you can help in developing countries to remove some small molecules, not salt necessarily, and then eventually you can remove bacteria, virus, so you can have a second life. So a tight membrane, looser membrane, people, as you and I talk, somebody dying somewhere in the world, Africa, from bacteria and virus poisoning than not PFAS.
Mm-hmm.
So those membranes could be applicable and people looking at those.
Okay. So a second life for them for a different purpose. Okay.
Instead of 10 years, now 30 years. Because the backing, remember, the backing is ultrafiltered. Now it will reject virus and bacteria.
Sure, sure. So yeah, still put it to use. So, and then one of the questions was the idea of this multi-barrier approach, right? Like, PFAS is just one of the things we're trying to get out of here. You've talked about it in the context of multiple kinds of treatment and pre-treatment, right? But a lot of folks that are new to membranes might think, well, yes, but if a membrane gets a tear or a membrane gets a hole, then it's as though it's not there. So how do we take care of the multi-barrier approach when we're dealing with membranes?
Well, membrane hole, it doesn't happen that often, depending what you do. And of course, our membrane, the functionalized membrane hole doesn't exist. It's already 100 nanometer there. But RONF type hole cause problems. Or hole means crack, So you put something in there which did damage, that will cause you serious harm, And but one thing I will bring it up, summarize. Suppose you give me pure water with 1,000 ppb or 1 ppb PFAS.
Okay.
And I mean, membrane rejects 100%. All. And 100 million gallon of water. You and I will go bankrupt tomorrow morning. You're pushing the water that much, that costs energy. So you need to concentrate by other approach.
Okay.
The reason is that you pass that water. You're not passing PFAS. But maybe in those cases, and different bottom line is that it is you're passing just water, millions of gallons. So for dilute PFAS, 30 ppb to 4 ppt, it doesn't work that way. That's where adsorption, sorption come in the picture.
Okay. Makes sense. Makes sense as a treatment train. So are there some rules of thumbs out there? I mean, in particular, when we think about co-contaminants, micro nanoplastics, you were mentioning TCE and other things out there. So what are some of the treatment trains starting to look like?
Well, microplastics or nanoplastics, somewhere in membrane, you have to have some microfiltration, depth filter, other thing has to be there,
Okay.
Otherwise, you'll reduce the life of your final membrane, whether it's functionalized, doesn't make a difference. Including activated carbon, you're going to have a problem, particles coming in. So that assumes that structure is already there someplace, many places, okay? Then followed by, you have to look at that, is the norms and things, surface water may have norms and other things,
Right.
how will that interfere with things? Do I need to remove? And sometimes NF membranes lose NF, could remove 90% of norms out, but PFAS may go through. I may look at on that one, PFAS going through actually,
Right.
and then look at that. So basically, if we take the water, the real dirtiest water, and put through the normal commercial RONF membrane, it is going to cost you. Serious problem.
Makes sense. Makes sense. And is there a fractionation among all the PFAS, we throw that out, but what we really mean is a big family of compounds, right?
Yeah.
So do the membranes fractionate across the different family of compounds?
Well, you saw RO, normally right now we take a good RO membrane, not this one. In NF, maybe PFB, the lower molecule, is about maybe, if you get 85% of those, 80%, other one you get 99.9, but that is not going to bring you to 4 ppt.
Okay.
Ever.
Okay.
So these guys in China, Australia, which I put down the paper, they try to bring that PFBA high.
Okay.
Our normal commercial membrane as exists today, PFBA is not high, the lower molecular rate. So maybe we do get the lower molecular go through and then use there to develop adsorption or ion exchange column for picking up the lower molecular compound.
Okay. Okay. And so you would follow with that.
That's approach could be. Because
Okay.
now you're capturing the molecule, not hitting the whole water.
Sure. Fair enough. So you do that on the concentrate stream then, or?
Anytime you have dilute stream, you capture.
Mhm.
And then you generate, concentrate. Rather than the entire, in the RO, you have to apply pressure, get the water go through.
Okay. Fair enough. So take home message, concentrate.
Yeah. And selective concentration come in the picture. Now, can I make a membrane tomorrow which rejects 100% PFAS and 0% or some small percent be a lower molecular, it has value possibly. But we go to all rejection of all, go to 4 ppt, most probably I will not be economically not viable.
Okay.
It'll be
Okay.
too tight membrane.
Okay. Well, DB, this has been fantastic. You have done an awesome job handling a lot of questions. You're brilliant as always, my friend. It's such a pleasure to be able to interact with
Let
you.
people know in the audience, if anybody feel free to contact me, I will be sending info if they can find something, and not just helping out people. My goal is to help people.
So you're offering your services if people have questions. They should just drop you a mail, and you're happy to do it.
And,
You
you know,
want
they
to
can, if it's important, my email address and my phone number there, important. I visit places, and I'm more than welcome to help out and not asking for anything in return. Intellectual helping people is my highest priority in life as a faculty. Giving intellectual, even some women come and say, what did you find and how do you modify? Give some ideas, They may not be successful, but they have to try it out.
DB, you're fantastic. Thank you so much, my friend. Marissa, we'll turn it over to you.
Okay, thanks everyone for all your questions, and thank you to Professor DB for sharing your knowledge with us today. We have several webinars planned in the near future. You can go to aaes.org/events and reserve your spot. And don't forget to register for the final wrap-up PFAS webinar scheduled for next Wednesday, January 29th. Just a reminder, if you're not yet an AAES member and you're considering joining the Academy, you can email me to discuss our membership options. For all board certified individuals, PDH certificates for this event will be sent out by the end of the week. That's all for now. We enjoyed being with you all today. Thank you so much and have a great day.
Thank you very much.